Hello everyone, this is Jacob Dow from Galil, and today we'll be talking about the control of step motors. The subject we'll cover include first the operation of step motors, and we'll talk about different driving methods such as the full step, half step, and microstepping. We'll also consider the merits of steppers in comparison to servo motors. And later we'll move on into the specific discussion of using steppers with Galil controller. We'll talk about the configuration, we'll talk about the feature of smoothing, the pulse rate, and the method of closing the loop. Well, let's start with the step motor operation. What makes motors move? If you take a phase of a stepper motor and energize it with some current, you produce some torque as a function of the position. And that torque tends to be sinusoidal, as you see here. Such a torque would cause the motor to move to the point P. And why is that? Because if you happen to be to the left of it, the torque is positive and would move the motor to the right. If you happen to be ahead of it, the torque would be negative, would take it backward. In either direction, you would end up with the position P. This point, the ending stopping point, is also known as the equilibrium point, and that's how step motors would force the shaft to move to a particular location. Now, that will only cause the motor to get stuck in one position. If you want to move further, you go to the second phase, phase V, and instead of energizing phase A as we had before, that leads to stopping at position P, now we energize phase B. That creates a different curve that moves us to point Q. So this way you could move the motor from one point to the other, from the equilibrium P to equilibrium point Q. Now to move further, obviously we cannot switch phase A again because it would take us backward. But what we could do is energize phase A with a negative current. That would create a torque curve that's the opposite of this. It would go negative and positive. Specifically, it's going to look like that. This is the torque curve, the dotted line one, that we would have if we energize phase A with a negative current. It's just the opposite of the original one. And notice that with that, the equilibrium point moves to R. So we managed to move from P to Q to R. To move to S now, we energize phase D with a negative current that moves us to S, and so on and so forth. Now the sequence then, in order to move continuously, we start initially with the current in phase A being 1 amp or some nominal value. That gets us to the position 0, which is here. The first step is done by switching to phase B, giving it 1 amp, and that moves us one step. Now we go to phase A and give it minus 1 amp, that gets us to 3.6 degrees. Now I go to B, give it minus 1 amp, that gets us to 5.4. And to continue on, we go back to phase A, give it 1 amp. That gets us to a new cycle somewhere here about 7.2 degrees. And by stepping the motors again and again and again, we could just move it indefinitely. This is the method of full step. Now, let's consider some characteristics of a stepper motor. The first one that characterizes a stepper motor is that it always has to be turned on. A stepper motor would produce a torque that is a sinusoidal function of the position. But because a stepper motor runs open loop, we don't know when we need a torque. As a result, we always make sure that the torque is available, and that's necessary. That could be done by energizing the phase at all times. This implies that the stepper motor is going to run hot because it's always turned on. Stem drivers would shut off, reduce the level of the current. Once the motor is sitting in one point, they would reduce the current to 60% of the value or something of that type, but still it runs always on. Another feature of a stepper motor is the resonance mode. Think about that. If this is the torque curve, and the motor happened to be at this position, and we energize phase A, there would be this positive torque that would move the motor forward. But as the motor is moving forward, it picks up speed. So by the time it gets to this point, it has some high speed. That's going to cause it to overshoot. and then undershoot and go back and forth a few times until it settles. This behavior of overshoot and undershoot indicates that the motor is going to be underdamped, and it leads to resonance. As a result, the stepper motor would tend to have a resonance frequency typically in the range of about 150 hertz, that it would like to overshoot at that frequency. And watch out, if you try to drive a step motor at that frequency, most likely the motor would oscillate and lose synchronization. That's a feature of a stepper motor when it's driven in full step. Now, in addition to this fundamental resonance frequency, it has to do with the magnetic interaction. A stepper motor has another mode of oscillation, another mode of resonance that's called mid-frequency resonance, and that happens somewhere in the mid-range, like about 1,000 RPM speed. It's a nonlinear phenomenon that is result of interaction between the driving circuit and the step motor characteristics and so on. It behaves like a black hole. You drive the motor, all of a sudden get sucked into this frequency range where it starts oscillating and loses synchronization altogether. This is something that, as I mentioned, is very nonlinear, but could be changed by changing the drive characteristics, changing the voltage, modifying the current loop, and so on, could solve that problem. Nevertheless, that's something one has to be aware of when dealing with stepper motors. Another characteristic, of course, is the fundamental operation of a stepper motor. Steppers were designed to run open loop. That's where they have an advantage that results in simplicity and low cost, but the other side of the coin is that due to the fact it runs open loop, if for whatever reason got stuck, it didn't move, there is no way for the controller and the host to find out. One more point to clarify, it's a position error. When we tell the motor to move to a certain point by energizing the phase, we expect the motor to move here. But if the system had some friction, for example, at that level, the torque would push the motor toward the equilibrium point. However, at some point when the torque equals the friction, the motor would stop, resulting in a position error, the difference between the stopping point and the equilibrium. The size of the error obviously is going to be a function of the friction mostly. There may be other factors that would affect that. So keep in mind, even though you're driving a stepper motor and expect it to stop precisely at the equilibrium point, there would always be some errors. The only question is how large they are, and they're determined mostly by the friction. Now, let's talk about a different mode of operation, the half-step. If we energize phase A, the motor would stop at point P. If we energize phase B, the motor stops at point Q. What happens if we energize both of them? In that case, the resulting torque would be the sum of the two curves, this sinusoid and that sinusoid, and the sum of both of them would be this dotted line curve. And this dotted line curve results in equilibrium point H, which is halfway between them. Another way to look at it is think about the two phases fighting. Phase A wants to keep the motor at P. Phase B wants to keep the motor at Q. Because they have equal power and equal torque, they settle on a point halfway in between. And that results in a half-step mode. This method obviously increased the resolution of a stepper motor by 2, because now we could move in half steps instead of full steps. And here's how the sequence goes. Initially, we energize one of the phases, would stop at the original position. Now we energize both of them, and we end up at a half-step point. Go to the second one, and we complete the step. And we could go on with this table, but obviously this would require twice the main transition, with the resolution being finer by a factor of 2. We could pursue this argument further. If we energize phase A, the motor stops here. If we energize phase B, the motor stops at Q. What if we made the currents in the two phases unequal? For example, we made the current in phase A full current, but in phase B, we made it only 20%. Obviously, phase B is going to be weaker, and in the fight between the two of them, phase A is going to win, and the equilibrium point would move closer to A. So by working out the proportions between the two currents in phase A and phase B, we could move the equilibrium point anywhere we need along this curve. And by working out the proportions carefully, we could refine the resolution, the stopping resolution very well, and that method is called the microstepping. In practice, it implies that instead of turning a phase full on or full off, we just control the magnitude. And we have DACs that control the current to phase A and phase B. And by working the equilibrium position would end up being the arctangent of the ratio between them. This method was developed in the late 70s, 80s, and by now it's very, very common. Now, what are the advantages of microstepping? The first obvious one is the improved resolution. Now we could divide motor evolution into as many as, say, 50,000 increments instead of the classical 200 increments, and improve the resolution, say, 256 times or so. Another effect is the reduced resonance. As we mentioned, the motor would tend to overshoot. Let's, just for the purpose of discussion, assume it overshoots by 50%. If you advance it by 1.8 degree a full step, it would overshoot by 9/10 of a degree, which is large. But with the microstepping, we take the 1.8 degree step, divide it, say, 100 times. Then when you ask the motor to move 100 of 1.8 degree, and it overshoots 50% of that, the amount of overshoot would be minuscule, and probably the effect of friction would be then more dominant to just eliminate that resonance mode altogether. So these are the advantages of microstepping. Of course, it doesn't come for free. It comes at the added cost because a microstepping driver happened to be significantly more expensive than a full step or half step. Now, at this point, we should say a couple of words about the comparison between stepper motors and servo. Obviously, the two technologies are valid. The two have place in the motion control industry. And in many machines, we combine them. We could drive 2 axes with steppers and 3 by servos and so on. So let's review the main features of those and when to use one versus the other. A stepper motor, you should consider that if you happen to have simple open loop operations. If you need to drive something over a distance, the operation is simple, doesn't have to be very precise, and if occasionally it stopped and failed, it's not the end of the world. In that case, that would be a good solution. Also, if you're really pushing for low cost, that may be one solution. Stepper motor, by their nature, they produce a reasonable amount of torque, but at low speed. Once the speed increases, the torque drops. So if you need to have a high-speed operation, they're not suitable for that, but for low speed, they would be fine. Another feature of step motors is that they like friction. They hate inertia and like friction. The more friction you give a stepper motor, the better it behaves, the less it would overshoot. So if you happen to have a system with friction, that would improve the odds of a stepper motor being successful there. Well, in contrast with that, the alternative, the servo motors, being closed loop, those are the ones you would use in high-performance closed-loop systems when you need extremely high speeds, not only about 3,000 or 6,000 RPM. So, brushless servo motors could go up to maybe 20,000 RPM or so. Also, if you need extremely high accelerations, those would be the ones. And if the system is such that it has disturbances in varying conditions and so on, this is where you need a closed-loop servo system and not a stepper. But as I mentioned earlier, there is room for both the stepper and for the servo, and the designer has to decide what are the merits of each technology. Component-wise, a stepper motor, most of them would have 2 phases, and the phases are isolated, so you would end up with 4 wires. 4 wires that are connected to the circuit that drives it, and the circuit that drives the stepper motor is known as the indexer. It has the power elements and the logic. Upstream would have the motion controller that issues the commands. The way the motion controller talks to the indexer is by 2 signals called the step and direction. The step is a series of pulses. For every pulse that appears on the step line, the indexer would increment the stepper motor by 1 step, or 1 increment. The direction would indicate whether we're moving forward or in reverse. So these are basically the elements that you would find: controller, indexer, and stepper. Now, when it comes to the Galil controller, if you would like to use a Galil controller to drive a stepper motor, there are a couple of things we'd like to mention here. First, because Galil allows every axis to drive either servo or stepper, you need to notify the controller that you would like to drive a stepper with that particular axis, and you do that by putting a jumper. It's called the SM, and SM stands for step motor. Putting a jumper at the right place for a particular axis to designate it as a stepper motor driver. Then there is an MT command that configures the pulse shape and the timing, and we'll talk about that. And another command you may want to consider is the smoothing function KS. So we'll talk about the remaining function, MT and KS. First, here's an example of a series of pulses and direction. What this is saying is that initially, while the direction is positive, the motion is forward. So we get 1, 2, and 3 pulses going forward. After 3 pulses, we reverse the direction, so the remaining pulses would be backward. That's a typical waveform. Now, when it gets to pulses of this type, we have to be careful. We have to ask ourselves, when do we consider the pulse valid? On the leading edge or the trailing edge? If we do that on the leading edge, then what we have here is confusing because the direction changes precisely when the leading edge occurred, and this may lead to ambiguity. So if we do it at the leading edge, we want the direction to change on the trailing edge. And the inverse is the same. If we look at the trailing edge and the direction change at that time, that's a problem also. So we need to define and be clear about whether the indexer would consider a pulse on the leading edge or the trailing edge, and the Galil controller would make sure that the change in direction would happen on the off phase. So if you tell the Galil controller, my indexer looks at the leading edge, then the Galil controller makes sure that the direction would change at this phase. The way to tell the controller which edge the indexer takes is through the MT command. When we tell MT minus 2, we say active high, or basically a leading edge. So we're saying the indexer looks at the leading edge, and if that's the case, if MT is minus 2, then the Galil controller would always make sure that the change in direction occurs at those times. If, on the other hand, the indexer looks at the trailing edge, you specify MT2, and Galil, of course, then would change the directions on the leading edge. Now, there is another variation here. You would expect that whenever the direction is positive, that implies forward. But forward could be to the left or to the right. And sometimes you may want designated differently. So in order to orient the signal with the direction forward and reverse, we have another variation. If you want the direction to be such that when it's positive it goes forward, use MT minus 2 and minus 2 and minus 2. If you want to invert it so that when the direction is positive and that would lead to a backward direction, which some people do, which is the reversed option, you just use MT minus 2.5 or 2.5. So basically you have two choices because there are two functions here, and the binary combination between two choices is 4 possibilities, MT2, minus 2, and plus minus 2.5. So this is the configuration of MT. Another function you may want to consider with the Galil controller is a smoothing function. When a digital controller generates pulses, you may end up with pulses that are not spaced uniformly. In the before diagram, we exaggerated with that, but that indicates a situation. You may have some pulses at some rate, and all of a sudden big gap, and some pulses, and so on. When those pulses are applied to an indexer, you're basically telling the stepper, move fast, slow down, fast, and so on. And as we mentioned, steppers don't like to change directions, change speed abruptly because they're underdamped. This may cause overshoot and loss of synchronization altogether. What the steppers like is this type of pulse. Very, very smooth, uniformly spaced pulses. All of them running at uniform space, indicating that the speed is constant. The Galil controller could take the original series of pulses and smooth it out to this form. And basically the way we do that is we take the pulse rate and put it through a low-pass filter. And the parameter that controls the low-pass filter is Ks. The larger you make Ks, the smoother the waveform would become, and the longer the time constant of the filter becomes. So this is a parameter that you as the user could select all the way from 1/2 to 64. Now, there is another function I would like to mention here. When pulses are generated by a digital process, due to quantization, there may be an error. There may be extra pulses here and there and so on. With the Galil controller, we didn't want to take any chance with that. So not only do we generate the pulses, we want to make sure that under no circumstance that there might be additional pulses. And to do that, we actually measure all the output pulses. We take all the output pulses and we read them back. And to do that, we use the auxiliary encoder port to measure all those pulses. This is why when you use a stepper motor, the auxiliary encoder port is no longer available to you for you to read other encoders. However, the main encoder is still available. So if you would like to connect an external encoder, you could do that through the main port. Now let me review some of the functions we have here. If you go to the Galil controller and say RPX, RPX refers to the reference position, that would tell you what the commanded position of the stepper motor should be. TDX, that's a dual encoder, that would be the number of the pulses that went out to the indexer already. Now TPX is the main encoder, and that could be a totally different sensor altogether. Now because TDX is the number of pulses we generated in response to the commanded position, RPX and TDX should be almost the same. The only difference between them is TDX is a smooth version of RPX. In other words, TDX is the output of a low-pass filter where the input is RPX. As a result, you would expect that TDX would lag slightly behind RPX depending on the KS parameters. Up until now, we talked about the fundamental operation of steppers and operation in open loop, which is the main purpose of stepper motors. Stepper motors were designed to be open loop. That's why they are, under those modes, they're low cost and effective. But in some cases, we may need to close the loop for reliability. Closing the loop involves two steps. First of all, you need to detect that there is a loss. You need to detect that there is an error. And secondly, once you detect the error, you need to take corrective action. And we'll talk about those two functions independently. First of all, how large of an error is an acceptable error? Let's assume that the stepper motor is supposed to be running at a certain rate, and at some point it's supposed to be at the position 0. But due to friction and due to the fact that it's still catching up with the target, it was a bit off, a fraction of a step. Is that okay? The answer is yes. Probably as long as the stepper motor is within plus or minus 1 step, that's okay, because if it was commanded to be at 0, but it was at minus 1.8 degrees, still the torque is pushing the motor in the right direction, and it would not lose that point. So an error of within minus 1.8 degrees or plus 1.8 degrees is definitely fine. You could even argue that even if the error was up to almost 3.6 degrees, it's still okay, because if the error was here, still the torque is positive and would lead the motor toward the right equilibrium point. So, but beyond 3.6 degrees is definitely no-no, because at this point, if the motor was here, the torque would be negative and would take it away to the next equilibrium point. So absolutely, within beyond 3.6 degrees is an error. Within 1.8 degrees is fine. Between them, it's up to the application engineer. And you should select that according to your application, because if you know that in your application the error is always a small fraction of a step, you could set the limit to that. Now specifically, how would you do that? In order to close the loop, you must add an encoder to the motor. You need to put an encoder on the motor shaft. And for the following discussion, let's assume that the step motor resolution is S steps per revolution. If it was full step, S would be 200. If it was half step, it would be 400. If you go to microstepping, you go all the way from 5,000 to 50,000. But let's say that you also added an optical encoder with a resolution of n counts per revolution. Now you need to compare numbers from the stepper motor and the encoder and make sure that they're following. And when you deal with large numbers, if you don't do the math correctly, you could end up with quantization problem and the whole analysis falls apart. What we recommend to do here is the following. Let's assume for simplicity when you start at the point where the step motor output position is 0 and the encoder is 0. So we're starting at absolute 0 position both on the encoder and the stepper. From there on, if you monitor the step motor pulses, the TDX, the pulses we output, that's the total number of pulses. If you divide it by S, the step motor resolution, you would find the position of the step motor in revolutions. Similarly, if you took the encoder pulses, TPX, and divided by N, the encoder resolution, you find the encoder position in revolutions. Now, ideally, the two quantities, the step motor commanded position and the encoder feedback position, should be the same. Any difference between them is an error, E. So E is the error, which is the difference between the number of revolutions the step motor is supposed to be doing and the number of revolutions that the encoder is reporting. So, but keep in mind, E is expressed in full revolutions. Now, how large of a value could E have and still be all right? If you have a typical step motor with 200 steps per revolution, then every step is 0.005 of a revolution. So as long as E is within plus minus 0.005 or 1 over 200, that would be fine. The minute we see that E exceeds this value, it indicates that the error is large, and that's an error condition. So the error detection is fairly simple. You put an encoder, read the encoder, compare its values to the commanded position, do the right math, and you would find the error. But the next step is, okay, what if I found that there is an error? How do I correct for that? What are the possible procedures? That's very much up to the designer. In some cases, we may say, look, if we develop an error is so severe that just shut down the system, stop the system, and notify the host. That's one possibility. Another one might be, wait until the end of the move, read the position of the encoder, and if there was a loss of pulses, make a correction at the end of the move. A third possibility is to make the corrections on the fly. This would be the case if you're performing operations such as engraving, cutting, and you would like the position to be right all the time. But this approach is somewhat risky because you ask yourself, why did the motor lose pulses to start with? Probably because it could not keep up with the command. Now, if you ask it to put on top of the command another higher speed to correct for an error, you may cause some additional problems and aggravate a situation that was bad to start with. So the third choice is something that should be taken very seriously, and you should be sure that the motor could actually perform the correction before you command it. But let's see an example how the second case works. Here's an application example. This program is written in the Galil language, and hopefully you're all familiar with that. First, we start with the label, and we define the two parameters. N is the resolution of the encoder, and S, being 50,000, is the resolution of the stepper motor indexer. We start with 0 position. We define the initial position of both the stepper and the dual encoder is 0. Now we command the stepper to move a certain distance of 200,000. At a certain speed of 500,000, we also define the acceleration, deceleration. Say begin. Now, the following trip point AMX would wait until that motion is complete. So we commanded the motor to move. Now we go to a label test. And first we could put a wait statement, in this case 20 milliseconds, just let the motor settle. This is something that could be modified according to the application. Once it's settled, we measure the error between the commanded position of the stepper and the position of the encoder. And as we mentioned before, the error is in revolutions. We'd like to make sure that the error is within plus minus 0.005. But because the error may be positive or negative, first we need to take the absolute value of that, and we do that through this command, the absolute of E. And next we check to see if the absolute value is within 0.005. If it is, we jump to the label that's okay, and that's the end of the move. If on the other hand we find out that it's not, then all we have to do is to make a correction. And the correction magnitude equal to E in revolutions multiplied by S, the resolution of that step. So this would be a certain number of pulses, for example, 723 pulses. Then we command the motor to perform an additional move, position relative of correction, begin that, and at the end of the motion, if we're still not certain, we could go through the test routine again and make sure that that correction succeeded. And we could theoretically do that a few times until the motor ended up at the right place. Well, that concludes the presentation, and thank you for attending.